In this portion of Lecture 4, we will discuss magnitude comparators and decoders. A magnitude comparator is a combinational circuit. Its job is to compare two values and to determine their relative magnitudes. It's a very important component because this allows us to determine which of two values is greater, and this makes a very big difference in our ability to be able to have if-else constructs as well as conditional loops. In this case, we're looking for one of three different outputs. We want to know if A is equal to B, if A is greater than B, or if A is less than B. We expect that one of these three conditions will be true, the other two will be false. Before we look to figure out how we will see if A is equal to B or A is greater than B or less than B, let's recognize that A is composed of 4 bits, A3, A2, A1, A0, ranging from the most significant to the least significant. And we'll do something similar for B, which will be B3, B2, B1, B0. We're going to define a variable called x sub I, where I'm going to AND together AI and BI. I will also AND together AI prime and BI prime. One of these two will be 1 if the two values are the same. What that means is if I take a look at this across all 4 bits, if I get 1 when I AND x3, x2, x1, and x0, I know that A equals B. To see if A is greater than B, let's look first of all to see if A3 is 1 and B3 is 0. If that's the case, since A clearly will now have a greater magnitude, then we know that we're going to have that A is greater than B. If x3 is true because the 2 bits have the same value, let's take a look at A2 and B2 prime. If those 3 ANDed together give me 1, then again I have that. If the top 2 pairs of bits are equal, then I'll take a look at bit 1 in both numbers. If all 3, then I'll look at A0 and B0 prime. Now in the case of A is less than B, we'll prime A's bits and not B's bits. If in the most significant place B is a 1 and A is 0, I know that B is greater. If the most significant place they're tied, I will look 1 over to the right. And if A is 0 and B is 1, we know B is greater than A, and A is less than 0. If those two places are tied, now we'll look at A1 prime and B1. And if not there, I'll look at the last place. This will tell me one way or the other whether I have A is equal to B, A is less than B, A is greater than B. One of these will be true, the other two will be false. Here you see the circuit for the magnitude comparator. You'll see all the way on the left, A3, B3, A2, B2, A1, B1, A0, B0. And you'll notice in every case, the appropriate pair are ANDed together. In every case, you'll see the complement of one and the normal form of the other. Now, these all go out to a NOR gate, so that from this we're getting x3, x2, x1, x0. The NOR gate, rather than giving us A3 XOR B3, will give us whether or not the two values match. And how we use them you'll see in the upcoming slides. You'll notice here that we have several of the lines made far thicker and also in grain. What you see in each case is how we calculate x3, x2, x1, x0. These all go together down to the lowest AND gate that you see there, and this produces A equals B. You'll notice here a different green line made broader, and this goes from A3 prime B3 into the OR gate on the far right. This is one of the four terms that we use to determine if A is less than B. In this slide, you see a different set of green lines. X3, showing that A3 and B3 are equal, goes into an OR gate, goes into an AND gate, together with A2 prime B2. So if the two A's are the same, and A2 is 0 and B2 is 1, we know that A will be less than B. Here you will see the thick green lines going from the OR gate for A is less than B, backward to an AND gate, and where you'll see going into the AND gate is X3, X2, and also the result of the AND gate that produces A1 prime B1. So if the third bits and the second bits are the same, we'll look to see the first bits, and if A's bit there is 0 and B's is 1, we know that A is less than B. Now we can see the last of the four lines going into the OR gate for A is less than B. It goes into an AND gate that you can see there in that long row of AND gates, second, third from the bottom. And you'll see it traces back to X3, X2, and X1. The other line goes to where A0 prime B0 are ANDed together. If the three upper bits are all matched, we look at this least significant pair of bits to tell us which is greater. We can do something very similar for the lines going into A greater than B, but it would follow in more or less the exact same way as this did. Now we'll take a look at a different type of device, namely decoders, something you'll find in most digital devices. A decoder is a combinational circuit. It converts binary information coming from n coded law inputs to a maximum of 2 to the nth unique outputs. The decoders in which we're interested in are what are called n to m line decoders, where 2 to the nth power is greater than or equal to m. Commercial decoders usually include an enable input, without which there is no response from the decoder. The truth table tells us a great deal about how a 3 to 8 line decoder works. If the enable is 0, it doesn't matter what the three inputs are. All 8 of the outputs will be 0. Once we allow the enable to be 1, it will look at the different 8 possibilities for input, depending on how we combine the three values, A2, A1, and A0. In each case, one of the D lines will be 1, the others will all be 0. 0, 0, 0 as an input will give us a value for D0 and 0 for all the others. If the inputs spell 0, 0, 1, it's D1 that will be 1 and the other 0, and so on. The idea is that one and only one of these will produce an output. Here you see the circuit diagram for a 3 to 8 decoder. You'll see that A0, A1, and A2 are all split between normal and complemented forms, with A2 prime going to D0, D1, D2, and D3. A2 going to D4, D5, D6, and D7. A1 prime goes to D0, D1, D4, and D5, while A1 goes to D2, D3, D6, and D7. A0 prime goes to D0, D2, D4, and D6, and A0 goes to D1, D3, D5, and D7. All the combinations are accounted for, and this way we can see which one of these output values we actually transmit through. We can construct decoders using NAND gates instead of AND gates. Since NAND gates invert the outputs, it's more economical to invert the signals coming in. E has a value 0 to enable the circuit and 1 to disable. and there is only one output D sub I that has a value of 0. Here you see the truth table for a 2 to 4 line NAND implemented decoder. You'll notice that for the one case where E is 1, regardless of what A1 and A0 are, we'll get all 1s for the D's, meaning that we did not have a value passed through. When E is 0, we will get one of the 4. You'll notice in every case for the A1 and A0, it is 0 that gives us a meaningful value, not 1 and the other way around. The 2 to 4 decoder looks very much like what we had last time. We have either 1 or 0 going to the various gates, and we'll have all 4 combinations accounted for. You'll notice again that the enable is inverted, so it's going to be a 0 going into the various NAND gates. Sometimes we may be looking for a particular decoder, but what we'll only find available to us are smaller decoders. Let's take a look at an example where we are looking to build a 3 to 8 decoder, but what we have available to us are 2 to 4 decoders. The less significant inputs are attached to both decoders. A2, on the other hand, will serve as E, the enable for the higher decoder, and E prime for the lower decoder. Here you see the diagram. In both cases, A1 and A0 go to both decoders. Now, in the case of the enable, A2 complemented goes into the lower decoder, and A2 goes into the enable for the upper decoder. If what I have, for example, is 0, 1, 0, I'm giving 1, 0 as the inputs, and the opposite of 0, 1, into the enable. That's for the lower decoder. So it will register D2 as the answer. The upper one gets, again, A2, gets the 1 for A1 and the 0 for A0, but it gets 1, it gets 0 for the enable. What it reads is that this is not enabled, and all 4 of the outputs on the second decoder will be 0. It seems that in constructing our 3 to 8 decoder in this fashion, we've sacrificed the ability to have an enable. That's not necessarily the case. What we can do is split the enable and have it ANDed with A2 prime for the lower and A2 for the upper. In this regard, we still have a 3 to 8 decoder built out of 2 to 4 decoders, and in both cases, the enables are still available to us.